Hello. As you can see here for video number 10, we're going to be going back and doing a modified version of question number 4 from the online sample exam problems for Actuarial Exam 1, also called Exam P. We're going to be using two rules that we have talked about that are really important: the addition rule for mutually exclusive events, also known as disjoint events, and the multiplication rule for independent events that we first talked about in the very last video, video number 9, along with some algebra to solve for the number of blue balls in an urn. There are going to be two urns that both have just red and blue balls in them, and we're going to want to find the number of blue balls in the second urn. If you don't happen to remember what an urn is, here's what one looks like. They're typically metal or ceramic, and typically they contain people's ashes, but in this case we're going to be thinking about red and blue balls and thinking about probabilities. I should also say before we solve this that, pretty much in every problem we've done so far, a Venn diagram was definitely helpful, and the problem could be solved with just a Venn diagram and thinking intuitively about probabilities. You really didn't need all the formulas that I have shown you, but I've shown you those formulas for a reason, and because they're going to be definitely helpful here. The Venn diagram is only marginally helpful. You don't even really have to draw it. I will, but it only helps you at the start of the problem to conceptualize one fact. Otherwise, we're just going to use some formulas, okay? So let's go ahead and we'll read the problem first, and then we'll start by drawing the Venn diagram. So you got an urn, the first urn, containing 10 balls, 4 red and 6 blue. And then a second urn that contains 16 red balls and an unknown number of blue balls. Okay, and that unknown number is what we're going to want to solve for. I'll go ahead and right away call it x here. An unknown number x of blue balls, and we'll be solving the problem for x. A single ball is drawn from each urn at random, one from the first, one from the second. The probability that both balls are the same color is 0.44. Okay, so they're either both red or they're both blue. We want to again calculate the number x of blue balls in the second urn. And that's where the problem statement that you find online stops, and that's what I'll solve first. But as I often do, I have an extra part here that is, I think, extra interesting this time. And something surprising happens as well. So you may want to hang on for that. The extra thing is if the probability that both balls are the same color is not 0.44, but an arbitrary number, lambda, between 0 and 1, how does the answer for x, the number of blue balls in the second urn, depend on lambda? But wait a minute, x has got to be a whole number, and lambda is arbitrary here. Will this definitely give us a whole number value for x? The answer is not necessarily. So we need to ask what values of lambda can this problem be solved for a whole number value of x, 0, 1, 2, 3, 4, etc. In a sense, by generalizing this, you are almost thinking of yourself as a test creator. This can give you infinitely many different test questions that are similar to this that you can ask people. We also want to try to ask and answer the question, how would all of these answers be affected if instead of 4 red balls in the first urn, there were R red balls in the first urn, where R is 1, 2, 3, 4, etc. And I will tell you before I start solving this now, that the extra interesting thing that happens when R equals 6. You may want to pause the video and see if you can figure out what interesting thing happens when R equals 6 and different values of lambda. I will, like I said, draw a Venn diagram. So a box, first of all, representing a sample space, but it's only going to be, again, slightly helpful. It's going to be helpful in conceptualizing the very first step of what we do. I'll think first about the first urn. The ball you draw is either red or blue and nothing else. There's no green balls or anything like that. Those events are mutually exclusive. They can't happen at the same time. So they're non-overlapping, disjoint. And in fact, since one of the two has to happen, their union is the whole sample space. So I could, instead of drawing circles here, I'm going to draw rectangles. I got two rectangles. This one, say, representing when the first ball out of the first urn is red, and this one representing if it's blue, R1 and B1. What about for the second urn? I could break up the sample space, partition it in a similar way, though I should do it maybe with vertical rectangles. This one here representing R2 when the second ball is red, and this one representing B2. Okay? So that's, again, not a typical way to draw the diagram, but it's something you could do here. And then if you think about the balls being the same colors, that means either they're both red or they're both blue. If they're both red, you're in the intersection of R1 and R2, which is this rectangle up here. That's R1 intersect R2. And then if they're both blue, you'd be down here. This is B1 is this rectangle, B2 is this. Their intersection is this smaller one. You'd be down there. Those are the ways that both balls could be the same color. And these two events are disjoint sets, mutually exclusive events. We can use that special addition rule for mutually exclusive events, okay, to find the probability or to describe the probability that both balls are the same color. And that's what we'll do right now. 0.44 is the probability that they are the same color. Symbolically, we can represent that as the probability of R1 and R2, intersection means and, or, union means or, B1 intersect B2, B1 and B2. They're either both red or both blue. Again, these are mutually exclusive. This is the sum of the probability of R1 and R2 with the probability of B1 and B2. So that's the addition rule for mutually exclusive events. I could maybe also call it the special addition rule that I use there. In general, you have to subtract the probability of their intersection. That's the general addition rule. But their intersection is empty, so its probability is 0. What do you do now? We're going to use the special multiplication rule for independent events. But wait a minute. Nowhere in this problem do you see the word independent. Is that a problem? It might seem like it at first, but it's actually not, because what you need to do, you need to realize, is you need to assume R1 and R2 are independent, and B1 and B2 are independent. And you need to realize you can assume that because that's a reasonable assumption. You're mixing these balls up, shaking these urns up ahead of time, and drawing the balls out randomly, say one at a time. What you pull out of the first urn, red or blue, does not affect what you pull out of the second urn, red or blue. Okay? They're unrelated to each other. They're independent. So you're really assuming independence. And as I mentioned in the last video, video number 9, that's something people do all the time when they apply probability in the multiplication rule. If it seems reasonable that two events are independent, they go ahead and assume it. Now, that assumption may or may not be accurate, and that's something to be wary of, but in this case, it definitely seems reasonable. So I don't have to think about conditional probability. The probability of one thing and the other is the product of their ordinary unconditional probabilities. Remember, there's a general multiplication rule that involves conditional probabilities. So that's the multiplication rule for independent events. You could also call it the special multiplication rule. And now it's just a matter of writing these things symbolically based on the givens and solving for x. What's the probability of R1? Drawing a red ball out of the first urn, 4 out of 10. 4/10 or 0.4. What's the probability of R2? Drawing a red out of the second urn. There are 16 red balls and x plus 16 total balls. This is 16 divided by x plus 16. The probability of B1 drawing a blue ball out of the first urn is 6/10 or 0.6. And the probability of drawing a blue ball out of the second urn is x divided by x plus 16. So this equals 0.44. We now need to solve for x. It's not too hard. We need to just, first of all, maybe add these fractions. They already have a common denominator. So I can write them as one fraction. 0.4 times 16 is 6.4, and then I have 0.6 times x equals x plus 16, or divided by x plus 16 equals 0.44. Multiply both sides by x plus 16, you'll get 0.44x plus 0.44 times 16, 7.04 equals 6.4 plus 0.6x. It's a linear equation in x now. Isolate x on both sides, on one side. So I could subtract 0.44x from both sides and also subtract 6.4. I would get 0.64 equals 0.16x. Divide both sides by 0.16, you're going to get x equals 4. That is the answer, and that's answer A on the sample exam problem that you can find online. Okay? 4 blue balls in the second urn. Now let's go to Mathematica and solve the more general question. And again, something extra interesting happens. What I try to promote when I generalize here is what I call functional thinking. So we want to think about these things in terms of functions, because then you can make graphs. And again, this has got the benefit of allowing you to solve infinitely many problems at once, and also to just make connections with things and to realize you can think about things in terms of functions. So first of all, I've got a step-by-step description of what to do here for video number 10, which is question number 4. So the equation to solve for x when the probability of both balls are the same color is this equation that you see here. Lambda equals 6.4 plus 0.6x divided by x plus 16. Just same equation as you saw a few minutes ago with a lambda instead of a 0.44. We want to solve that for x. Thinking functionally, in other words, if we define a function f of x by that formula there, what we're really after is the inverse function, x equals f inverse of lambda, that will allow us to find the answer x for any value of lambda. And we are also wondering when the output x is a whole number, 0, 1, 2, 3, etc. So now you just do the algebra. Okay, so you multiply both sides of this by x plus 16 to get this equation there that goes over 2 lines. And then you would I would do 2 steps here next. I would subtract 0.6x from both sides, subtract 16 lambda from both sides, and then actually the third step is factoring out the x on the left side like this. Then divide both sides by lambda minus 0.6 to get this. And this is going to work and give you an answer as long as lambda is not equal to 0.6, as long as we're not dividing by 0. But it doesn't necessarily give you a whole number answer. To find when x is a whole number, it's probably best to plug x equals 0, 1, 2, 3, etc. back into the original function to get these numbers. So these would be the first 5 solutions for lambda when x is a whole number. Now remember, we're really trying to solve for x. So it's these values of lambda, 0.4, this thing 7/17, 0.42 with the 2 repeating, that would give you x values that are whole numbers. So if you were creating a bunch of different exam problems like this, these are the lambdas that you could use. And here's our old friend, the 0.44 right there. Okay? If you like, you can also realize that the limit of these things is 0.6 of the lambda values. So there are infinitely many values of lambda that give whole number answers for x, and those are these values of the form like this, and I've used an n here to emphasize that the input is a whole number. Okay? Non-negative integer. All right, let's make some graphs. We aren't to the extra interesting thing yet. That's at the very end. I did put in fractional values for 6.4 and 0.6 here and solved to get the same answer here for x in terms of lambda right there as we got up here, just written slightly differently. And I can think of that as the inverse function of f, and then I can plot it. Okay, so what we have here is a graph that helps you see the infinitely many different answers of this problem for infinitely many different values of lambda that give you whole number values at least. The answer really is represented by the second graph over here. X, this was the answer for x in terms of lambda, this formula that you see here, 32 minus 8 lambda over 5 lambda minus 3. And you can see you can get infinitely many different values based on that formula in this graph. The black dots are when x is a whole number greater than or equal to 0. This graph is the graph of the original function as a function of x, and these whole number values give you the corresponding values of lambda that you would then want to use if you were designing exam problems. Okay, just a couple different ways of thinking about it. All right, now we're on to the general part that has the unexpected thing happen. If there were r balls in urn 1, here are the relevant calculations. So first, this is the right-hand side of the probability equation that I wrote down by hand based on using the special addition rule and special multiplication rule. It simplifies to this. Notice it depends on both r and x. You should take a moment to think about this. And this thing is a function of r and x. However, I want to think of r as a parameter and x is the quote-unquote true variable here. So in mathematics, I'm plugging it in like this. And to solve for the answer in terms of for x, I need to solve that equation for x. The answer does depend on both lambda and r. If you plug in r equals 4 here, you should get the same answer that we got before. And you could also plug in lambda equals 0.44 to get the same answer that we got on paper, which was x equals 4. But now I can think of this as an inverse function of this, thinking of it as a function of lambda with a parameter r. And I can make a graph that I can animate with manipulate. And here's what you see what happens. So first of all, this is actually when r equals 1, so this is not the answer to the question, the original question. I can increase the value of r to 4, for example, and this now represents the original question, at least when lambda is 0.44. Right about here, x is 4, you go up to there, that dot represents the answer to the original question, as does this dot right here. But watch what happens as r keeps increasing. R is 5, then r is 6. Wait a minute, what happened? The blue graph on the right went away. I mean, the black dots are still there, but the blue graph went away. And then I go past 6, and then x as a function of lambda becomes a decreasing function instead of an increasing function. So something weird happens at r equals 6. If you haven't yet, maybe you want to take the time now to see if you can figure out what's going on. Let me now summarize what's going on here verbally. I'm describing it this way. When r equals 6, something strange happens. In this case, there's only a solution when lambda equals 0.5. You can see when r is 6 here, the lambda value is 0.5, 1/2. And any value of x can actually produce this solution. So x can be infinitely many different things, which is kind of hinted at maybe by these black dots here, although you don't see the blue graph. Also, however, when r is 6, if lambda is not equal to 0.5, there's no solution for x. Okay? And in fact, when you plug in r equals 6 into this formula, these two things will here and here will cancel as long as you're not dividing by 0. So you'll get negative 16 when lambda is not equal to 0.5, so you're not dividing by 0. But if lambda is equal to 0.5, this is 0 here, and so the fraction's undefined. If lambda equals 0.5, that doesn't tell you that infinitely many different values of x actually work, but it does hint at something weird going on. Okay? So I hope you found that interesting. See you in the next video.